Hi, thanks for attending the webinar on vector database. So before I kind of start off in terms of explaining what database, I just wanted to take a minute and talk a little about the data volumes, which has been increasing in the past decade or so. So obviously this report is a little outdated, but the numbers for 2023 and 2024 would be falling the same range. So we are at as per as this report, when it was taken in 2020, we were at approximately 64.2 zettabytes of data, which is consumed worldwide. And what we're expecting, uh, by 23, 24 to be about 147. So almost double of what we are kind of looking at. Typically, 147 zettabytes of data. Typical use cases that we've seen in the data world, this compare, this contrast, the search, you find relationships in the data, you try to find patterns, you try to find anomalies in the data and outliers, and there are many more such use cases. Now, if you're really understanding the crux of the use cases and the problems that what we're seeing with the data and why there is a need for a system which makes data more easily representable. uh, I talked to the use cases and we talked about 120 zettabytes of data growing at 30% per annum. And so the problem, given the volume, the veracity, the velocity of the data, there needs to be a more intelligent system to represent the data, something which supports basic use cases such as compare, search, and find relationship. Now, we can go back, if you really kind of go back to the computer systems of representations of alphabets and numbers in terms of ASCII. So we had everything from A to Z and A to Z in terms of smaller case and then 0 to 9 digits, which is supported from an ASCII, and that's how eventually we kind of used it for representation of the text more at the machine level. Obviously, that goes down to bits, and usually we start with 8 bits for representation from an ASCII. So while we're taking cues from the same thing that we kind of look at representation of numbers from an ASCII standpoint of view. If you really look at the language, it's kind of made of text, and text is made up of words. Words generally have meaning and context. Now, the whole intent is we start with representing the words as numbers, such that the words which are similar by nature are in close proximity. So, something like a dog and cat both happen to be domesticated animals, so they probably could have a number which is similar by nature. And then once you actually have a series of words, then context applies to the sentence so that you can use match to take the sum of all the weights of the numbers to arrive at what the meaning of the sentence. So obviously, there are some words in the sentence would be more important than others. That's where the attention kind of, so you kind of put attention on those words and you increase the weights on those words, so they have a heavy weightage compared to what you would expect in comparison to the other. Embedding is essentially something. It's a number representation of all the known words in the language, and such that uh, from the representation standpoint of view, what we've seen is uh, you know you can actually see in the graph out here in terms of man and woman are represented around a certain uh, straight line format with some common coordinates, basically because they all happen to be humans by nature. And similarly, you have king and queen. Sorry, the KIN has got cut off. Uh, and then you have the verb tense, which can be used for walking and walked and swimming and swam. So effectively, the direction that we're going is basically trying to have some kind of numeric representation from a word standpoint, such that the meanings of the words, which are similar by nature, they're kind of grouped to close by one another. Similarly, you can see the country and capital, Spain and Madrid, Italy and Rome. So there is some level of connection. And obviously, while we talk in terms of three-dimensional axis, when comparing of words, they can be applied with multi-dimensional axis, and obviously where each axis represents some aspects of the word. And similarly, there could be 10 axes, 10 axes, so basically 10 dimensions. So basically, it kind of comes to the point where I can use a 10 dimension vector to represent a word, and basically, you know, the word, can have similar meanings across dimensions, and that's how the words which are similar to one another generally end up being grouped together. So embeddings basically is a map. So technically, so I want to just kind of get over little bit of the technicality. Embeddings is the mapping of a discrete categorical variable to a vector of continuous numbers. Neural net embeddings are low-dimensional, learned continuous vectors representation of discrete values. Neural net embeddings are useful because they can help reduce the dimensionality of categorical variables and meaningfully represent categories in the transform space. They help in finding nearest neighbors, so basically something which is similar or happen to be in the same embedding space. And that's how the whole recommendation base kind of comes in as an input to machine learning for supervised tasks and for visualization of concepts of relationship between categories. Now I'll take a minute and kind of go a little bit into vector database, because ultimately vector database is uh, is basically storing of the text into vector embeddings, and then that is being stored into the database. And so basically the context and the application goes through an embedding model that gets converted into a number representation, and that's eventually stored into a vector database. And when you actually query the application, you go to query based on your actual text, which eventually will get converted into the corresponding vector, and that's been used for comparison, because a numeric comparison is a lot more faster than text-based comparison. So that's how it really kind of boils down to. So if you have number representation of the same words and eventually the sentence, and then just compare it across a series of words, it becomes a lot more easier. So why are we going into vector database? I'll kind of talk to that in a minute. So typically, the use cases of the vector database, we've seen large language models. So generally deal with a lot of language and text, and obviously for them, every time to basically convert the text into numerical representation, then operate on them becomes quite cumbersome. So it'd be good to have a vector database, of whole Wikipedia and etc., for training your own LLMs. But obviously, I don't expect you to train your own LLMs. You would probably be in the business of extending an LLMs by tuning or transfer learning or something of that nature. A lot of AI and ML use cases typically, we are dealing with, we are kind of going into an area where we're going to have a lot of AI decision making. So most of your applications would be churning out a lot of data, and it'll be good to kind of start pushing the data into vector databases, and then basically straight away use that for AI and ML. So that's use a sizable chunk of compute cost from an embedding conversion standpoint of view. It's quite high, so it's a good thing to kind of do that and have it stored and then eventually kind of use it. And eventually in the long run, I wouldn't say that you're going to phase out databases altogether, but I see largely that's the direction which is possible. So the normal RD, PMS, etc., and all of it will kind of get phased out, and then eventually it's best to kind of have everything as a vector database. Then the expectation from a vector database will be a lot more from an access management and security standpoint of view. But some of the vector databases today actually do provide that. I'll talk about different databases in a minute. Typical business cases, what you've seen is basically discovery, for example, HR, job search, food discovery, and many more, chatbots, and all this more. So these are some of the use cases of vector database. Uh, a typical vector database which are available in the market, some of it could be open source. These are some of the. So basically, I've used Milvis. Milvis is a out and out open source, pretty good to use. You can basically set up your own Milvis instance and then eventually kind of go from there. But there's a lot more in terms of setting the cluster out if you're actually kind of going from a deployment stand. Pinecone comes most it's cloud hosted. It's a good one again. Its ability in terms of doing semantic searches and a lot of other areas from similarity standpoint view is pretty reasonable. Chroma, it's a standard document databases. It will just take the documents and convert most of them and embed, and store them up. Face, Quadrant, and Superbase are some of them. I'll basically walk into the Pine demo. So here I have, the code specifically for Pine is fairly straightforward. You just need to inherit the Pinecone client and basically set the corresponding indexes. And once you're having done, we have, we can, create the index if the index has not been created. And eventually you can send a bulk load of data frames. In this case, I have, kind of broken those data frames out and the corresponding words and then embedded the specific record. And I can go ahead and then insert or upsert the vector into that. Similarly, once you've kind of entered the data, you obviously want to query the data. So here's a method to query. It's pretty straightforward. You take the query, just encode it, and send the query to the index, and eventually you can get the results, and that's how the response. So now we take a minute and try to run this code. So before I kind of get into the running piece of the code, the data which is kind of being sent out is a series of department, finline, customer data. So in this, the customer specific data is for South American region, and their customers from the various cities in Brazil. So what we done, and the data has been uploaded. So here I'm just going to say, give me 5 customers from Sao Paulo. So I'm going ahead and querying the data based on this thing, and I'm sure if it does understand, great. If it doesn't, then probably yes. So you can see it kind of basically understand, but not holistically. So it's kind of pulled the data for customers from Sao Paulo, but it's also kind of pulled data from other, you know, the other areas as well. Similarly, I could ask, give me vendors from region from Sao Paulo. Hopefully, it should try to give me something. In this case, is bombed. So probably something has gone wrong in this case. Maybe try running this code once again and see if this. But in short, you kind of get the gist in terms of it's a fairly straightforward thing. Similarly, you could end up using Milvis. Milvis. Okay, I'll take a minute and also kind of talk. So the advantage what we've seen in Pinecone, sometimes you land up with data which is numeric in nature, and you could potentially also want to kind of send the numeric data. And the way to store numeric data without losing much of the context is to convert it can basically convert into time vectors. And so there is so basically Pinecone will be in a position to support time series data, and you could be then query the data on time series for trends and etc and all of that stuff. And this is the code for that. So I'm going to be checking this code in GitHub, and you can go ahead and then kind of use that.